Now we come to problem 10.3. We have a human skater, and we assume that the human person is a cylinder, which is perhaps not very friendly. Here are her legs. And it rotates about the center, which I call the center Z, with angular velocity omega 1 in the beginning situation. The mass of the person is m. And the person has arms, length L, and there is at each end a mass m. L, and here is a mass m. The moment of inertia about the axis Z in position 1 equals 1/2 mr squared, which is the moment of inertia of the cylinder, plus 2ml squared, whereby this is obviously the additional moment of inertia due to these two arms. Now the person pulls her arms in. Let's assume that she is not cheating and that there are no external torques here at the eyes, which I'm not so sure about at all. And so I'm going to get an IZ2, which is again 1/2 mr squared. But when these arms have been brought in, and these masses are at a distance little r, this is capital R, sorry, then I would have plus 2m r squared. And that's the moment of inertia which it is right now, and this moment of inertia is less than IZ1. If the person pulls her arms in and is not cheating here, then I Z1 omega 1 must be I Z2 omega 2. In other words, angular momentum is conserved if there are no external torques. And therefore omega 2 must be larger than omega 1. If you take a modest case, whereby the person's weight is 60 kilograms, no insult implied, and you take L equals 1 meter, and you take M equals 5 kilograms, and you take R equals 0.2 meters, then you will find that this portion of the moment of inertia is only 1.2, and that this portion is substantially larger, is 10. And so in the new position, this again is 1.2, but in the new position, this is only 0.4. So the moment of inertia has enormously decreased. The moment of inertia has decreased by a factor of 7, and so omega 2, which is the omega after the person pulls her arms in, is about 7 times omega 1. So she rotates about 7 times faster, which is by no means trivial. If you look at the situation of kinetic energy, you will find to your surprise that the kinetic energy has increased. It's immediately obvious because the kinetic energy of rotation equals 1/2 I, about the z-axis, omega squared. Now I omega is constant. So if you take the kinetic energy in situation 2, when the arms are in, divided by the situation when the arms are not in, you will find immediately omega 2 divided by omega 1, which is approximately 7 in our special case, because I omega is constant. Where does this come from? Well, as this person is holding her arm stretched, let me do it this way, she will have to pull on her arm to hold that mass in her hand and making it go around in a circle. And we call that force the centripetal force. Here are her fingers, here is that mass, and there is a centripetal force necessary to hold it in. And the distance over which she moves it, S, is also in. Now this is provided by her muscles. So it's clear that she has to do work as she moves this force closer to her body. And it's exactly that work that shows up in terms of kinetic energy.